Alright, so we're talking about Jordan-Holder series, and first of all, let's start off with a remark. Not every group has one. So let's take an example. Let's just take the integers. And so let's find a normal subgroup of the integers. Well, a non-trivial normal subgroup of the integers. Well, the integers are abelian, so every subgroup is going to be normal. So that's not a difficult thing. So, but we want the quotient to be simple too. So let's just look at 2z, just the integers, just all even integers. So, yeah, the quotient is z mod 2z, and that's abelian, so well, yeah, it is abelian, but it's simple because it's only got two subgroups, itself and the trivial subgroup. So clearly that's going to be, the graded piece is going to be simple, and so we have that. But then, let's see here, so 2z, let's think of a good example of a normal subgroup of that, which will give us a trivial quotient. Well, how about 4z? I mean, certainly 4z is a subgroup of 2z. It's normal by abelianity. And let's see here, the quotient is going to be, let's see here, 4z mod 2z. Well, that's again just going to be z mod 2z, and we know that's simple. And so, let's see here. So that's 4. How can we write 4? 4 is 2 squared. And then we have 2 cubed z. And then we just keep going. Okay, so this doesn't prove that it has a Jordan-Holder series by itself. Let's say instead of 2, let's put p here, where p is some prime. Then z mod pz is going to be the quotient here. And that's going to be simple because the only subgroups are z mod pz and the trivial subgroup. So let's call this P1 and call this P1, P2. And then we're going to keep going. So, all right, so P1z mod P1, P2z mod P1z is going to be isomorphic to z mod z mod P2z, which again has only itself and the trivial subgroup as subgroups, and so it's simple. And remember that these choices are sort of forced on us because all subgroups of z are of the form just nz for some integer n, and we're forced to choose prime numbers here in order to force these quotients to be simple. Yeah. So we just keep going, and then we're going to get P1 through PNZ, then we keep going, and obviously this never terminates. So we're never going to get a, we're never going to get a Jordan-Holder series out of this. Okay, so that's a fact. However, it's not so bad. Every finite group has a Jordan-Holder series. And this is a really easy induction argument. Well, it's not even really induction. All you do is you take a finite group and you consider the maximal normal subgroup of our set G, or a maximal normal subgroup of our set G. And so you find this maximal normal subgroup of G, and obviously you could just search through them. Like, it's a finite group, so there's finitely many subgroups. So one of them is going to be a, well, first of all, so one of them will be a maximal normal subgroup, and if E is, if the trivial subgroup contains just the identity element is your maximal normal subgroup, then you just tack on E to the end of this, and you've got yourself a Jordan-Holder series. Otherwise, you'll find some maximal normal subgroup in there, and because it's a maximal normal subgroup, if you consider the quotient from the group that you started with and this maximal normal subgroup, then it's going to be simple, because if it weren't simple, then there would be some something in between them, but then that would be a maximal normal subgroup. And that would contradict your choice of your maximal normal subgroup. And also, since this maximal normal subgroup is strictly contained in the group that we started with, then the order is going to be strictly less than the order of G. And so then then once you have this maximal normal subgroup of G, you choose a maximal normal subgroup of that subgroup. And you do the same thing. If it's E, you're done. If it's not E, then you've still found something that gives you a simple graded piece, and its size is going to be less than the size of the larger thing. And then you just keep going, and you can only continue this, like if the group has size n, then you can only possibly do this like n many times, or it might be n minus 1 or n plus 1. I might be off by 1 or something, but it's certainly finite. You can only do this a finite number of times, and eventually you're going to get to the identity, and you're going to have yourself a Jordan-Holder series. So there you go. All right, so now let's do a theorem. Any two Jordan-Holder series are equivalent. Okay, so for proof, I'm going to be a little hand-wavy in parts of this, but I'm going to try to be as clear as possible. So, let sigma 1 and sigma 2 be Jordan-Holder series for some group. For some group G. Okay? By the Schreier refinement theorem, they have equivalent refinements. We'll call them sigma 1 prime or sigma 1 1, I don't know, and sigma 2 1 respectively. See here, we're not going to have any more of these, so I'm going to make that a prime. So just to be a little more clear, I'll write them as like a slanty dash instead of a vertical dash, so that you see that it's not 1. Okay, so we have a refinement sigma 1 prime of sigma 1 and a refinement sigma 2 prime of sigma 2, and sigma 1 prime and sigma 2 prime are equivalent refinements, or they're equivalent. Okay? Let's see here. So either sigma I prime equals sigma I, and this is for I can be either 1 or 2, or sigma I prime is obtained by repeating terms in sigma I. And that's because sigma I is a Jordan-Holder series, so each of its graded pieces are simple. And so if you're adding in more things that happen to be normal, like if you want to add in a subgroup between two subgroups in sigma 1, and so you want to add that in and you want to have that normality, well, these two, the quotient of these two subgroups is simple. So if you're going to stick something in between them, then one of those two quotients that you end up with is going to be trivial, and so it's going to be equal to one of the two things that you started with. Okay? So then, what do we have? It's going to be a little bit hand wavy. GRI sigma J prime G is going to be equal to GRI sigma J G union just E repeated some number of times. And we're going to call this thing EJ. So here, J is either 1 or 2, and the GRI's, I ranges over from 0 to whatever the last GI is in this particular composition series. So then, why is this true? This is true because if you look at the graded pieces of sigma J prime, then for any two of the subgroups there, either you took them from sigma J without throwing any duplicates in there, in which case the graded piece just comes straight from sigma J. Or if that's not the case, then it's the case that these two subgroups that you have, you got them, one of them came from, well, one or both of them were obtained because you threw a whole bunch of extra subgroups in there. And so every time you throw a subgroup in there, what you're going to get is you're going to get a these two subgroups are the same, and so the quotient is going to be just the identity. Okay, so we've got some of these which came from sigma J, and note that all of these graded, since sigma J is simple, all of these graded pieces are simple, and in particular they're not the identity. So we have this description for the graded pieces of sigma J prime. Since sigma J prime is equivalent, I'll write just one squiggle for like an equivalence. Is this an equivalence relation, like in the typical sense? Obviously, any composition series is equivalent to itself, and yeah, it is an equivalence relation. Okay, so sigma 1 prime is equivalent to sigma 2 prime by construction. We have, so if EJ is the number of times that the identity appears in the graded pieces, so yeah, that's EJ. So then E1 has to be equal to E2 because we have a bijective we have a one-to-one correspondence between the graded pieces of sigma 1 prime and sigma 2 prime. So every time the identity appears in sigma 1 prime, it's also going to appear in sigma 2 prime, and vice versa. So the number of times it appears has to be equal in both cases. And thus, the fact that the collection of GRI sigma j, no, here. The fact that GRI sigma j1g is equal to GRI sigma 2 prime g, and these two are equal because the refinements are equivalent, implies that, well, if the identity appears the same number of times in each of these, then if we throw them all out, we'll still have the same thing left over. But what is left over if we throw out EJ here? We're just going to get this. And so GRI sigma 1g is equal to GRI sigma 2g. But then what does that mean? That means that the number of elements in here has to be the same as the number of elements in here. And it also means that for every GRI1 sigma 1g, there is some I2 in here such that GRI1 sigma 1g is equal to GRI2 sigma 2g. And what that tells us is that the graded, we have a one-to-one correspondence between the graded pieces of sigma 1 and sigma 2. And the fact that these have the same size tells us that sigma 1 and sigma 2 have the same size. So hence, sigma 1 is equivalent to sigma 2. And that's exactly what we wanted. Any two Jordan-Holder series are equivalent. And so this is really useful, and this also kind of shows why I prefer to work with the definition of a Jordan-Holder series, meaning that any graded piece is simple, because looking at the graded pieces tells you a lot of information about the composition series. And so if you know something, so if you know the graded pieces are simple, then you have a lot to work with. And we saw that in a lot of the stuff that we've done, is we use the simplicity a lot. But anyways, regardless of that preference, we have this proof that any two Jordan-Holder series are equivalent. And I hope that this explanation was clear enough, even though I didn't even write out the composition series for sigma 1 and sigma 2 and sigma 1 prime and sigma 2 prime. Because we have so many composition series floating around, I don't want to have to write them all out because that gets very burdensome. But hopefully this was sufficiently clear, and then we've finished this proof, and we'll move on and talk more about composition series.